In the last session, we created the factor groups in two ways. One is by using a homomorphism from a group to another group with kernel H. Then G over H, the collection of all cosets of H, is a group under the binary operation defined as AH times BH is equal to ABH. Here what we noticed is H is a normal subgroup of G. Now without using homomorphism, if H is a normal subgroup of G, then again G over H, the collection of all cosets of H in G, is a group called factor group or quotient group with the same binary operation. Now what we want to do is we are going to create a homomorphism here. So the theorem is this. Let H be a normal subgroup of G, then gamma from G to G over H defined by gamma of A is equal to AH is a homomorphism. So what we need to do here is we'll take two elements from G and see whether this gamma obeys the rule of homomorphism. So let A comma B belongs to G, and that implies gamma of AB is equal to, by definition it is ABH, and we know that if G over H is a factor group, this is AH times BH, and that is equal to gamma of A times gamma of B. So this is a homomorphism. And what is a kernel? The kernel of gamma is H. Why? Because if X belongs to H, gamma of X is equal to XH, and that is equal to H. And this is the identity of G over H. So what is the definition of the kernel? The kernel of gamma is equal to all elements from G such that gamma of X is equal to H. So the kernel of gamma is H. So we can write that is a homomorphism with the kernel H. us do the fundamental homomorphism theorem. So it's actually combining the homomorphisms and the factor group and all this other homomorphisms. So let phi be a homomorphism, be a homomorphism from G to G prime with the kernel H. Then phi of G is a subgroup of G prime. So what we have is, we have G here and we'll take it as a phi of G, and this is our phi, and we have a G over H here, and we know that there is a homomorphism. Just now we proved that there is a homomorphism from G to G over H, and we also know that there is a isomorphism here. This is a collection of all cosets of H. So if you take a element from here like A of H, that will map to phi of A. We already have done this, and this is actually called mu. So then if gamma is a homomorphism, this is actually our gamma, from G to G over H by gamma of A is equal to AH, then phi of A is equal to, phi of A is equal to what? Mu of AH. And what is AH? AH is equal to mu of gamma of A. So this is the fundamental homomorphism theorem. There is nothing to prove. We already know all these components. All we did is we combined all this together. Now let us derive a equivalent conditions for a normal subgroup. So let us say let H be a normal, or H be a subgroup. Let H be a subgroup of G. Then G H G inverse belongs to H for all G in G and H in H. Then the following conditions are equivalent. Second condition is G inverse equal to H for all G in G. third condition is Hg is equal to Gh for all G in G. And this is the condition for a subgroup to be normal. So if you can prove any of these, then you can say that H is a normal subgroup. So let us start with proving 1 implies 2. So we need to prove that if this is true, then this is true. Well, what is this? G inverse, by definition, is actually G inverse for all H in H and G in G. But this is already in H, so we can say that this is a subgroup of H. Now we need to prove that this is H is a subgroup of GH G inverse. So let us take then G belongs to G and H belongs to H. This implies G belongs to G means G inverse belongs to G and H belongs to H. And that means G inverse HG belongs to H with the condition. Because see, there is a difference between this and this. Here it is G, here it is G inverse. But if G is in G, then G inverse is also in G. So this is true. And that means, so this is an element in H. And that means G inverse HG, G inverse belongs to H. Because this is an element from H. And that implies H belongs to that implies, see, that belongs to GH, G inverse. Why? Because the definition of GH, G inverse is this. This is actually an element of H, and this is G, and this is G inverse. So that implies H is a subset of G, H, G inverse. And that implies H is equal to G, H, G inverse. And that is what we want to prove the next one. Now let us try to prove 2 implies 3. So that means G, H, G inverse equal to H for all G in G. So let H belongs to H. And that implies G, H, G inverse is equal to H1 for some H1 in H. And that implies GH is equal to H1G. And where is GH? GH is in G capital H. So this actually belongs to HG. Because this is from H and this is from G. So this implies GH is a subset of HG. Similarly, HG is a subset of GH. And that implies HG is equal to GH. Now let us prove 3 implies 1. So what does that mean? HG is equal to GH. So let H is equal to H belongs to H. That implies HG is equal to GH1 for some h1. So that means h is equal to G h1 G inverse, and that definitely belongs to H because this is H, and that's what we want to prove. Now let us define an automorphism and derive a condition for a subgroup to be normal. So, first definition is an automorphism. A isomorphism from a group G to itself is called an automorphism. In other words, automorphism is a bijective homomorphism from a group to itself. Now let us define a special automorphism. Let G be a group and G belongs to G. Define IG from G to G by IG of X equal to Gx G inverse. Then IG is an automorphism. So I am going to leave it to you as an exercise. Please verify. We need to verify this in homomorphism. We need to verify this bijective homomorphism. It's an automorphism called inner automorphism. And IG of X is called the conjugate of X by IG of X is actually, that means Gx G inverse is the conjugate of X by G. Now, the definition of IG of, okay, let us take a subgroup. Let H be a subgroup of G. Then IG of H is defined by G H G inverse H belongs to H. And that is nothing but G H G inverse. Then we also know that if or H is normal, if and only if G H G inverse equal to H. And that means, and implied by IG of H is equal to H. So the condition is H is normal if and only if H is invariant under all inner automorphisms. Invariant means it doesn't change. IG does not change H, the subgroup H. IG of H is equal to H. It is invariant. So this is another condition for a subgroup to be normal. We will do another definition here. A subgroup K and H are conjugates or conjugate subgroups if there exists a G in G such that the inner automorphism of G, inner automorphism based on G of K is equal to H. Now there is a result based on this conjugate subgroups. That result is, or problem you can say, conjugacy is an equivalence relation. So let G be a group and H, K and L are subgroups of G. Then first condition is it's reflexive. That is, H is related to H because E of H is equal to H or EH, and that's equal to H. It is symmetric because let H is related to K, that implies IG of K is equal to H for some G in G, and that implies IG inverse of H is equal to K, and that implies K is related to H. Now transitive. Let H is related to K and K is related to L, and that implies G1 of K is equal to H and G2 of L is equal to K. So that implies what does this mean? This means that K is equal to G1 H G1 K inverse, and L is equal to G2 K G inverse, G2 inverse. Now we will replace K here. That means G2 G1 H G1 inverse G2 inverse, and that is equal to G2 G1 H G1 G2 G2 G1 inverse, and that implies H is related to L. So the conjugacy is a equivalence relation. So we will do a small problem also. Find all conjugate subgroups of sigma 0 mu 1. See, sigma 0 and mu 1. What is mu 1 square? Mu 1 square is sigma 0. So this is really a subgroup. So we need to find out all the other conjugate subgroup of this. So how do you do that? See, we can ignore this sigma 0 because that is going to come in all the subgroups of all the subgroups conjugate to this. So we need to find out the conjugates of mu 1. So how do you find the conjugates of mu 1? Let us take sigma 1 mu 1 sigma 1 inverse. This is a conjugate of mu 1. Is a conjugate of mu 1. And what is sigma 1 inverse? Sigma 1 inverse is sigma 2 because sigma 1, when you compose with sigma 2, you get the identity. So sigma 2 is so this is actually equal to sigma 1 mu 1 sigma 2. What is mu 1 sigma 2? Mu 1 sigma 2 is mu 3. So this is actually equal to sigma 1 mu 3. And what is sigma 1 mu 3? Sigma 1 mu 3 is mu 2. So what we need to do is replace sigma 1 with all other elements. All you are going to get is the conjugates of mu 1, the conjugates of mu 1 are mu 1, mu 2 and mu 3. You won't get any sigmas. So the conjugate subgroup of sigma 0 mu 1 are sigma 0 mu 1, sigma 0 mu 2 and sigma 0. Now we will do a problem. Let H be a normal subgroup of G and M is equal to the index of G over H. This means that G and H are finite groups. G is a finite group. Then show that for any A in G, A to the power of M belongs to H. So what is the meaning of the index? M is equal to G over H implies the number of cosets of H in G is M. And that implies this is the order of the factor group. This is the order of the factor group. And factor group is a finite group because H is finite. G is finite. This implies for any element here, its mth power is going to be the identity. This implies for any A in G, AH to the power of m belongs to, or A to the power of is equal to H, the identity. And that implies A to the power of m H is equal to H, and that implies A to the power of m belongs to H. We'll do a problem. A subgroup C of G is a commutator group commutator subgroup if X belongs to C implies X is equal to A inverse B inverse for some A comma B in G. So every element of that subgroup is expressed as A, B, A inverse and B inverse. Now show that G over C is abelian. Before that, we need to show that C is a normal subgroup, which I am going to leave it to you as an exercise, because otherwise this is not a valid factor group. So what we need to do is take two elements from here. So let A C comma B C belongs to G comma G or C, and that implies AC inverse is equal to A inverse C and BC inverse is equal to B inverse C. So we'll multiply this AC times BC times AC inverse times BC inverse is equal to A inverse B inverse C, and that is equal to C. So what does this mean? AC times BC is equal to, let us take one by one. AC inverse equal to BC is equal to BC times BC, BC times C, and that is BC. One more time, AC times BC is equal to AC times BC, and that is equal to AB. Sorry, you are multiplying on the other side, so this will be BC times AC, and that is equal to BAC, and that is equal to B, or you can say write it like this. So this implies G over C is abelian.